I would like to welcome you tonight to our second public lecture in our series, the Pacific Northwest Earth Science Lecture Series, which is a mouthful. And when we're trying to decide what to call this, we had several people sitting around the table brainstorming about names. And when we put together the email for people to sign up for reservations, the person handling emails in the department said, well, why don't we just call it Geolecture? It's like, well, of course, that was a great idea. So anyway, we may change this to something a little easier to say. But I do want to point out that this is co-sponsored by the Research Center, which has a short name, GeoMap Northwest, which is also the Pacific Northwest Center for Geologic Mapping Studies, which is hosted or resides in the Department of Earth and Space Sciences at the UW. It's also co-sponsored by Department of Earth and Space Sciences here at the university and the U.S. Geological Survey. So tonight's topic, Mount St. Helens. It's a fun topic, it's an exciting topic, and if we geologists had to pick one icon that we could put on our desktop that would represent geology, it would be a volcano. I mean, what else says geology like a volcano does? To anyone who thinks about becoming a geologist, they want to study volcanoes. And I can't think of a better person to talk to us about volcanoes than Steve Malone. He's been a seismologist and has been studying volcanoes and earthquakes as they relate to volcanoes for something like 40 years. And specifically, he's been talking about and studying Mount St. Helens for over 25 years. And I think he has a right to call that his volcano. In fact, back in 1980, he was involved with a lot of the public, all of the media interaction related to the activity as it was apparent that Mount St. Helens was going to erupt. And he was one of the scientists who was actually willing to stick his neck out. And as I hear from him, it actually didn't get chopped off because he was willing to make predictions, he was willing to speak to the media and actually speak out when he felt that there was real danger. So I feel very honored to have Steve Malone here tonight to talk to us about Mount St. Helens. So with that, I'll turn it over to Steve.
Thank you, Kathy. That's a very kind introduction. Indeed, I'm under no illusions that actually you came this evening to hear the speaker, but rather it's because of the topic. As Kathy said, volcanoes, well, perhaps next to dinosaurs, are the most popular thing in earth sciences for the general population, particularly kids. Volcanoes grab one's imagination, and in our case we have one right here in our backyard, so I consider ourselves quite fortunate. Not only, I mean, we have lots of volcanoes in the backyard, but we have one that's currently active. And so I think this topic is one that lots of people like to follow, and as we'll see this evening, we can make it possible for you to do so essentially from your home. When this topic came up and Kathy asked about my presentation, it's what's next? And that brings up all sorts of different questions. My friends and colleagues and even acquaintances often are asking questions too. And so I think I'll start off with just reviewing some of these types of things that come up. When will Mount St. Helens erupt? What sort of eruption will there be? What are the hazards of that eruption? And in fact, how do we tell anything about what's going on remotely? And there are other volcanoes in the Cascades besides St. Helens, so we need to think about those as well. Well, maybe I'll just start off and answer all these questions right now and just get it over with, and then we can go on with the program. The first question, when will Mount St. Helens erupt, is really not a very good question because it is erupting right now. that's currently erupting and has been since last October. So really the question that people want is, when is it going to explode? Well, the answer to that is it's not going to explode, at least not big, in the next few weeks, at least. Maybe longer, and it will explode again sometime, but we can really only look so far into the future, and at this point we're only willing to say, on the order of weeks to months, it's not going to explode. What sort of warning will there be? Well, we will see precursors to it. Very much like we have in the past, we think we'll see changes that will tell us that it's in that mode where it could explode. And by explode, I mean explode big, not these little bitty things that just throw ash around a few thousand feet, but something that's really hazardous. But what will the hazards be? Most people refer to that as, will it be like May 18 of 1980? Will it devastate a large area? Well, that type of an eruption that had the lateral blast, that's not going to occur again, possibly for many decades, if not centuries. The geometry of the situation, as you'll see later, just isn't right for that type of an event to occur. But a lot of ash going up, hazards to aircraft, hazards right around the volcano, yes, that certainly can occur again and will within years to decades. Now, how do we know all of that? Well, I'm not going to answer that right now, because what I'm going to do is take you through a number of the different ways that we monitor the volcano, and then how we try to interpret what's going on based on those data. And I'll finish up with a brief look at some of the other volcanoes in the Cascades. Now, this will be a personal perspective. I'm a seismologist, and so you're going to get a little bit of an overdose of earthquakes, but quite frankly, they are the most important aspect of monitoring volcanoes. At least I think so. And really what I want to hopefully leave you with is the feeling that science is not essentially the answers or the facts and the figures, but it's rather a process. It's asking the right questions, taking the observations that you can make. Based on those questions, come up with a mental model of what you think is going on, and then test that mental model against additional observations. So it's a process, it's an ongoing process, and I hope you'll see from this presentation that that process is going on right now, and indeed you can sort of think along with that process as it develops. So we'll do that by reviewing the last 25 years at Mount St. Helens, and from that you'll build up what types of things we've learned. We'll start back in 1979, before 1980. And actually, we really should start before then. But at this point, we could ask the question, do we know what Mount St. Helens is going to do? Well, yes, we can sort of, in the sense that the climatologist can say, well, it's likely to rain more often in Seattle than it is, say, in Tucson. So on average, we know something about what volcanoes do, not necessarily any specific one. So the geologists go out and they look at all the different volcanoes. From those data, they can get sort of an estimate of how often and how big they've erupted. And for the Cascades, they come up with sort of a plot like this, north to south. And you can see from the little baby volcanoes lined up over the last several thousand years that Mount St. Helens has been very active, certainly compared to the others. In fact, there's hardly a time that's gone on for more than 200 years without an eruption, and many of them quite sizable. Well, that's determined by the geologists looking at the rocks in the field and sort of taking apart the layers, looking back to determine this. Well, several geologists in the mid-1970s, after completing this work on Mount St. Helens, said, wow, this is an active guy. In fact, it hasn't erupted in 150 years, so I think there's a pretty good chance it could erupt even before the end of the century, 1975. They were right. Well, let's look at it in a slightly different way. There are lots of different types of volcanoes. And over on the left, there are the names of the rock types associated with them. But the main thing, they're ordered essentially in how viscous the magma is. And the viscosity of the magma and the magma type is generally related to how often the volcano erupts and what the precursors to an eruption are, i.e. what is the unrest period before it goes boom. And at one end are very viscous magmas, rhyolites, such as you'll find at Yellowstone or Long Valley caldera. And it's millennia between eruptions, many millennia between eruptions, and long periods of unrest before they erupt. At the other end are the very fluid basalts, like in Hawaii. And those eruptions can come pretty frequent, and the precursors to those can be a matter of only hours or days. Well, in between are the types of volcanoes we have in the Cascades, and those are dacite to andesite, sort of in between, relatively viscous, and they have inter-eruption periods on the order of centuries and precursor periods on the order of months. And St. Helens lies right there. So we can see that, now, there's sort of a corollary to this. This is a general type of relationship. In addition to this, there's how long has that volcano been at rest so far? It determines something about how the precursor will go. If it's been quiescent for a long time, generally the precursory period, the period of unrest, is longer and more intense before it finally erupts. Well, let's move to St. Helens. The first earthquake of the precursor to the big eruption in 1980 took place on March 20th. I don't have a seismogram for that. It was recorded on film, and that doesn't show up on this type of plot very well. But a couple of days later, we do have the seismograms for a station that's located just on the flanks of the volcano. And you're going to see seismograms several times in this presentation, so I'll take a moment and explain it. It's a time recording of how the ground moves. And very much like a book, you read it left to right and top to bottom in increasing time. And the very regular little marks there are minute marks, so it's 1 minute between those. And the irregular sort of fuzzy blobs on there are earthquakes, small earthquakes. And I think it's pretty obvious that over this period of March 22 to 23, that there was an increasing number of those events over the course of this 48-hour period. This definitely got our attention. The first earthquake got our attention, but rather than like an earthquake aftershock in which the smaller earthquakes follow in decreasing numbers with time, in this case, the number of earthquakes was increasing. Well, about this time we said, well, this is what might be a classic precursor to a volcanic eruption. Well, the following 2 days, it really got our attention. The activity became so intense that the station located near the volcano essentially was saturated all the time. There were so many earthquakes, so large, occurring one on top of another, that we changed and started monitoring visually a station 100 kilometers away up near Olympia. And even there, you can see there's lots of activity that can be recorded at that greater distance. Well, at this time, in consultation with the volcano hazards experts of the USGS, I decided we needed to say something publicly that this really was a precursory signal to a volcano. And so on the 26th, it did go public. It made the paper on the 27th. This was in the day of big hair, so. And soon, Mount St. Helens eruption soon. Well, soon is a nice word, right? Geologically speaking, that could be centuries. Luckily, it turned out that this was published in the morning of the 27th, and at noon that day, it erupted. Man, I'm good. Wow. Geez, I must be a seismologist or something. So, the first activity take place. The seismologists were going nuts with the earthquakes. Now the geologists could get excited because there was dirt in the air. These types of phreatic eruptions continued on and off for the next 2 months. And I say phreatic, that's a term mostly meaning they were steam explosions. They were hot water heated by magma coming into the volcano, possibly magnetic gases and things mixed in, that would then come bursting out, carrying bits of the volcano along with it. And these continued for quite a while. Well, in response to this, in fact, in the first week, we established some additional seismic stations, and later on, when we had access to helicopters, we took some up high on the mountain. In this case, established a station on the Dog's Head, which is up at 8,000 feet, and this was a sobering experience. No, maybe it wasn't that sobering. I'm not sure what's in that. I can't remember what's in that bottle. But the earthquakes are continuing during this period as well. And they were very strong up there, and strong enough that it didn't feel like you could stand up. Anytime one occurred, you wanted to get down and hang on to Mother Earth. Because right next door, some tens of meters away, there was a bulge growing. A whole side of the mountain was expanding under the pressure of magma from underneath. To illustrate that, this picture was taken on March 21st, the day after the first earthquake. And if you keep your eyes sort of on the skyline there, just to the right of the highest point, it's going to fade to a picture taken on May 1st, about 5 weeks later. I think you can see that jumps out at you and to the right. This is the bulge. It's growing at about this much, 1.5 meters per day. Now this is solid earth moving that much continuously. And what that is magma is moving up into the volcano and pushing out this section of it. And in the process, of course, it's generating lots of earthquakes. Earthquakes are the fracturing of rock, and this magma pushing into the volcano is fracturing rock. Well, there were a lot of discussions about what the implications of this were, and scenarios were many in the discussions with the volcanologists, and seismologists participated as well. They went all the way from, well, a new dome would form here. Just the lava would come out nice and peacefully. Maybe there would be some smaller explosions. There might be big vertical eruption columns. There might even be a failure of this unstable north side of the mountain, and it might slide down and go all the way to Spirit Lake. Wow. Well, we know from what happened on May 18th, starting at 8:32 in the morning local time, that side of the mountain did fail. An earthquake occurred, generated an avalanche that uncorked the magmatic system underneath, came bursting out, high velocity, generating a blast cloud that went much further than Spirit Lake. It ended up, this picture taken from Mount Adams, going 30 kilometers. Probably 3 times further than the worst case scenario that we had come up with before that. So it was 30 kilometers wide, and the cloud rose 30 kilometers high, and of course was blown east. Well, the seismic record of this event is somewhat interesting. Same type of seismogram. Again, at the top you see something labeled volcanic LF, or low frequency earthquake. This is the type of earthquakes that were occurring very frequently for the past 2 months. Nothing unusual. Well, at 8:32 in the morning, listed here as 15:32 because seismologists deal in Universal Standard Time, GMT, another earthquake has started. And it went on shaking the ground for over 10 minutes. Now, this was an earthquake followed by or triggering a landslide, triggering a blast, and the debris flow flowing down the area. Well, when that was over, in the first 15, 20 minutes or so, the seismic record shows what is labeled here relative quiescence. It was still shaking some, but not nearly like it had been. And then about noon that day, it starts shaking more. And in fact, at this point, the volcano starts erupting like sort of a well-behaved volcano should, vertically. And a large quantity of ash is coming out at this point. Pyroclastic flows are coming out on the north side, flowing almost to Spirit Lake area. That goes on for almost all afternoon. Around 5 it shuts off, and we have deep earthquakes going on. So I'm showing this seismic record because as we go along, we'll see we can interpret some of those parts of it for what they are. This area labeled harmonic tremor is really eruption tremor. It's noise from the expanding gases in the magma, pulling the magma and tossing it out the top. And that's a pretty noisy process seismically. But afterwards, they're deep earthquakes. In the precursory period, all the earthquakes have been shallow. Afterwards, deep. Now that's sort of as counterintuitive. If the magma is coming up from the bottom, you'd think it should have deep earthquakes first and then shallow earthquakes, because it's moving up. But that's not the way it works. The precursors have shallow earthquakes following the eruption, then they're deep ones. Well, when it's over, 2.5 cubic kilometers of the mountain is missing, as it wasn't blown into the stratosphere, as some news reports indicated. The vast majority of that is in the valleys down below, as a debris flow that flowed down the Toutle Valley about 16 kilometers, partially filling in Spirit Lake. And of course, a large area devastated, and a number of people killed. 57 people died, including a friend and colleague who is participating in the monitoring effort, David Johnston. Well, we felt pretty down at this point because we had hoped that we would be able to anticipate such an event in the hours or a day ahead of time. And indeed, we didn't. And in fact, reviewing the data, looking back again, there really wasn't anything that led up to this other than the 2 months of very intense activity. So we had plenty of warning. We had 2 months of warning. But on the socially useful scale of hours to a day or so, there was no change. So here's the duration of that precursor, which doesn't fit into the way we like to make decisions. And there was a lot of pressure toward the end, even though a large area was evacuated around there. There was a lot of pressure to allow the loggers and the homeowners, et cetera, back into that area. And that was mostly resisted. Most of the people that died were actually outside the exclusion zone because they were further away than the worst case scenario indicated there was a problem. So here's a lesson. The worst case scenario can, on some cases, be exceeded. Later on, there were more eruptions. That summer, several other explosive eruptions, and in these cases, we could see changes just preceding them in the socially useful timescale. And again, mostly it was through seismology, though later on, geodetics and gas chemistry played a role. Early on, it was the seismic monitoring, in which changes in the earthquake activity, both size and kind, would give us an indication of what was occurring. And we would sort of sum up the energy in these earthquakes and plot those over time, and it would show us a curve that had this funny upkick to it, and then an eruption would occur. And we used these sorts of data then to make an announcement, in some cases hours and later on days ahead of time, that an eruption such as this was occurring in the summer of 1980, relatively small compared to May 18, but still plenty big enough to get your attention. It would have been very hazardous to aircraft in the area or anyone that was right on or very near the volcano. That winter, the activity changed a bit. It went from explosive eruptions to more quiescent or quiet types of eruptions in which viscous lava would be placed in the crater, forming a dome. But we again saw these types of increases in activity, in seismic activity, as precursors, and could recognize those at the time and give a warning that one of these eruptions was going to start. Well, later on, they even got more obvious, and we had more time ahead of time. Early on, it was just hours ahead, then days, and by 1982, we would have over a week of indication that something was coming. And in these cases, these later ones, there was geodetic monitoring as well as gas chemistry that participated in this. So we thought we're sort of starting to see what was going on here. Well, we'll summarize then the last 25 years of seismicity, and particularly at their depths. The eruptive period of 1980 to 1986 is in this outlined in green, in which most of the seismicity is relatively shallow, less than 3 kilometers deep. Though you see these periods in which there's quite deep seismicity also. That's the earthquakes that just follow the explosive or relatively explosive eruptions. So again, this model of the precursors are shallow, and right within the volcano itself. But soon as an eruption has occurred, you get these deep events. Well, we've modeled those as a relaxation. Suddenly the pressure in a crustal magma chamber, where the magma resides for some period of time, suddenly that pressure is reduced because a lot of that magma has gone out the top. That sudden reduction causes some shifting or readjustments in the rocks around it. Those rocks are brittle and they fracture, and that we record then as an earthquake. So it's sort of backwards from what you'd expect. As the precursors start, you get the shallow events because that's breaking of rock at the top of the magma column. Once the eruption takes place and the pressure is reduced, you get earthquakes deeper. Well, what about then following 1986? Well, for a few years there was a period of quiescence, about 86 to 89, and then we started seeing these periods of deep earthquakes. Well, this really didn't make sense at first, but then we realized these are slightly different than the ones just following an earthquake. And in fact, we could interpret them in terms of a resupply. New magma coming into the system, but not coming out the top. So it's repressurizing. And when it does that, again, we get earthquakes being generated. Follow up on that, several students have worked on this problem over the years. In fact, one of the first ones to do so is now the head seismologist at the Cascade Volcano Observatory in Vancouver, Seth Moran. But here's an example of doing some high-precision relocations of some of those earthquakes. And the gray ones are shallow, and in this case, the black ones are deep. So you can see they're spread out over a larger area than the shallow ones, which are just under the dome. Well, if we take cross-sections here and sort of flip it up on edge, we can look at this in cross-section. You see some structure. There's sort of this narrow part at the top and then spreading out in two different areas in the bottom. So we can model that sort of conceptually by putting a magma chamber in there that right after an eruption contracts a little bit, generating earthquakes. And then as that magma chamber is replenished, pressures go up, it causes fracturing around it afterwards. And in fact, if you study the earthquakes in details, you can determine something about the stresses and orient what the major stress component is using something called focal mechanisms. And you can see they're different in different places. Again, making one of these mental models, then, we sort of fit in where the magma chamber is, that elliptical-looking thing in the middle, causing failure on faults around it, and sometimes the same fault moves in the opposite direction on different parts of the fault. It's sort of being wedged apart. And the earthquakes seem to be supporting that type of model. So it looks like for the last 18 years there were these periods in which it was replenishing, but not coming out the top. So here's the seismologist view. Of course, it's got to be simple. Seismologists are. Precursory seismicity up here at the top of the magma system as it starts to break its way through to the surface. After an explosive eruption, you get the earthquakes around the pressure-reduced magma chamber. Then there's something I haven't talked about at all and we really don't understand very well, but there's some special earthquakes called deep long period events. We think they're associated with the feeder supply system down deep in the crust, but we really don't understand them hardly at all yet, but we're working on it. And finally, now we realize there are these repressurizing earthquakes in the same area as the post-eruption seismicity, but with a different sense. So now we can see both ends of the volcanic cycle. Well, going from the early 1980s, when there was a small dome, it grew through 1986, and then essentially languished there until fairly recently. During this period of time, every late summer, early fall, I would take a group of students and we would go hiking in there, sort of as an orientation trip for new students. I called it the Dance on the Dome trip. And indeed, we had one planned last fall on September 25th to go in to do the same thing. And of course, we keep an eye on the seismic records just to make sure everything is okay. Well, I'm going to show you the seismic records of that period now. September 22nd, absolutely quiet. September 23rd, we start seeing a few little events here. Now, this station is not the same one I showed you before. This station is located actually on top of the dome in the crater, SEP. So it's very close to the action. So it can record even little tiny earthquakes, and these indeed are very small. Well, as we saw this increased activity, I decided, ooh, maybe we better postpone this trip. This doesn't look good. So about here on the, late on the 23rd, I said, okay, we were going to leave on the 24th, drive down there to do the hike on the 25th. Let's postpone. We'll wait a day, go down on the 25th for a hike on the 26th. The next day, I looked at the record. There's even more of these things. Damn, I better cancel. So we canceled the trip, and we watched the records for a while. Oh, geez, it looks like the seismicity is going away. Why did I cancel it? I was dumb. Well, on the other hand, if you wait long enough, you maybe made the right decision. Whoa. Okay, it came back with a vengeance. At this point, there's no question, St.Helens, this is shallow earthquakes, small and shallow earthquakes, the classic sort of precursors again. Well, we look at it sort of on a larger scale. Probably many of you were here and saw the news reports, and the papers and the TV went nuts, of course. We came out with information statements to begin with, and then there's now sort of a hierarchy of alert things. Everything's got very official, going from yellow to orange at one point. And so again, we put out warning, and the newspapers pick these things up. Notice that it says here, small to moderate steam and ash eruptions called most likely. I like this. This is indeed what we said was the most likely. We also, having been burned badly back in 1980, included a whole range of scenarios, saying these are not very likely, but the volcano could do all these things. And we put them all out there. And the media often would pick up on the most dire or dramatic and report that. In this case, the paper did a very good job of saying what we really were saying. The most likely was this. And indeed, this became pretty obvious when just behind or just south of the dome, we saw deformation taking place. Flying over it, the glacier that had formed back there started to break up fairly quickly. And indeed, this paper came out on Thursday, September 30th. On October 4th, or 1st, boom, first big explosion. Wow, we're good. Did it again. And it was exactly what we thought might occur, a fairly mild steam and ash explosion. Got a little video clip showing some of that. Some of it's using an IR, infrared type of camera to try to get temperatures in there, but a lot of it is just visual filming. And you can see this isn't an explosion. It's not like a bang. It's more of a whoosh, sort of a continuous feeding or pulsating explosions that are relatively small, constantly throwing out this dark material, which is mostly old rock. And this goes on, in this case, several minutes, putting up a nice cloud and making the news media very happy. Unfortunately, it destroyed our seismograph station. The station that was on top of the dome, SEP, got hit by flying smut and rocks and debris, and it was beyond repair. So we had to replace it. So let's look again at one of the things that was perplexing at this point is the explosion itself only lasted a few minutes, but it was not very seismic. This arrow is pointing to what we think is the explosion signal. It's relatively small compared to all the earthquakes that were going on beforehand. As soon as the eruption really got going and was over, all those earthquakes stopped. And there was a period of quiet that lasted several hours. And it was quite confusing that afternoon looking at the records that had been banging away with earthquakes very frequently, every 20 to 50 seconds, and now nothing. Was it over? Nah, it's not over. It's coming back. And indeed it did, and even stronger. And then the next day, we had a period of what is called volcanic tremor or harmonic tremor. There was no eruption, yet there's a constant, strong shaking of the ground. At that point, we said, whoa, we don't know what's happening. Maybe the small ash and steam explosions is wrong. It could get bad, so we went to a level red. And red is bad, big. And there were lots of different stories going on, what might happen, how big it might be. But it went away, and then the earthquakes came back. There was other periods of tremor. There was other small explosions took place over this period of time. And the media had a field day. I think at one point there was something like 19 satellite trucks all lined up there taking a picture of a dusty volcano. Well, let's summarize now the sort of this first few weeks of the eruption from a seismologist point of view. Starting over at the lower left is when the swarm began. It pulsated at a low level for a while and then took off very actively. We had a first explosion about a week after the first signs of seismicity, followed by periods of strong volcanic tremor, followed by lots of earthquakes, several other explosions, and then it starts dying back down again. And then on October 11th, a new magma or new lava was first seen. And it was behind the old dome. If you can see, this is the old dome in here, and this little blurb back here is mostly uplifted ice, but in there you could see that there was some new, fresh rock, magma, or lava in this case. And the seismicity then just has continued more or less at a moderate level compared to what it was in the early period for weeks to months since then. Just a picture of that and a little test here, if you can sort of, for scale of what's going on. This is a picture of the new dome taken several weeks after it first appeared. You're supposed to find the ash here, and of course this gray stuff up in this area is, but here, this is the ash over here on the ice and snow. Now, where's the helicopter? That's the helicopter over here on the right. Little tiny thing. So for scale, you can see this isn't insignificant. All of this is the glacier that had grown behind the new dome being uplifted and just broken apart, just torn up. Well, let's go back to some seismology. We've been monitoring St. Helens all along, all this time. We knew something was going to happen again. In fact, quite frankly, I thought it was going to happen sooner than this. I didn't think it would last 18 years without anything going on, but it did. But we had a nice network there. Well, as soon as this activity started again, stations were upgraded, new stations were added, until it's very well monitored now, including a number of stations that are actually right in the crater. Now that's a hazardous place to work, and so it's tricky to get seismic stations in there. So techniques have been developed to do so with minimal risk, and those have been called spiders. It's a box with all the equipment mounted on legs, 3 legs, partially to get it up off anything that's hot so that the box isn't cooked directly, partially for the stability of that 3-point landing. And under it, you can see this thing it's called a Marv's lander. Marv is the name of the guy that built it. And it's a big block with seismometers glued to it that is independent of the rest of it. It's slung underneath. So that if this box is blown around in the wind, the seismometer is going to stick right down on the ground, and it's going to record ground motion, not the box shaking around. There's a GPS antenna on there. This is sort of like your little handheld you can have, except this receiver is very accurate. And if you process the data thoroughly, you can get locations down to better than a centimeter in its location. So it can track where this spider is put down, and if it moves, where it goes. There's an antenna, radio and antenna for telemetering the data back, so it's all in real time. And then, of course, there's the electronics and the batteries and power for it all in there. And there's a series of cables that are hooked to it so that you don't have to carry this thing yourself up there. Instead, you turn it on in the parking lot, you grab it with a helicopter on a sling, and you fly it up there, you plop it down, and release it. So the exposure to the helicopter is maybe 30 seconds rather than a person being up there digging holes and establishing a station, which normally can take hours. So a pretty nifty type of thing. And the GPS has turned out to be very interesting. One was actually plopped right down on the growing lava dome. And we started calling this thing a whaleback because it had this very smooth surface I'll talk about later. And this station was nicknamed Ahab. And can you find it? There's a station sitting on that now. It's right there. And we zoom in. See? I think you can see it there. It's a little three-legged guy sitting there. Well, this one we plopped right on the growing lava dome and then watched its GPS track. And it moved along. It lasted a week before it sort of fell off a cliff and was lost. But that week, it traveled over 80 meters, a little bit up and to the southeast. So this guy was trucking 80 meters in a week, and it's sitting on rock. So that whole thing has been moving that far during that period of time and sending back seismic data as well. Pretty neat stuff. Well, there are other GPS or geodetic types of things as well. There's been several placed around the outside of the volcano. These are even more accurate than the ones living on the spiders. These things can have resolution down to millimeters. And there's one on the south side that suddenly started moving back in November of last year. And it happened to be just about the time that this growing lava dome ran into the south crater wall. And it seemed to be actually pushing the wall out slightly. This is very reminiscent of 1980 when the bulge was growing on the north side. That one was moving at 1.5 meters a day. This one moved a total of 2 centimeters over the course of several months, and then it stopped. So, very different scale, but maybe the same type of process that was going on. Well, back to seismology. One of the fascinating things was all these earthquakes. By the way, by this time, we've had over 500,000 earthquakes recorded. Our seismic analyst is going nuts. Actually, we stopped analyzing all of them. She refused. She said, no more. Instead, we just sort of do visual analysis of a subset of those and train the computer to do summary information on all the rest. But there was a period back last fall in which very strong earthquakes, magnitude 3 earthquakes, were popping away at about 1 every minute or so. And one of the fascinating things about these, and even some since then, is that they're identical to one another. They're almost clones. Well, if earthquakes are the breaking of rock, then that must fracture the rock. How can you fracture it again in the same place? Well, there's a process going on then that breaks the rock and it stops and heals and then breaks it again in the same place. This is a process that's not very well understood, but it apparently is going on in this case. In fact, we think that what we're seeing there is the magma coming out. We're seeing the actual eruption process taking place in the earthquakes. Here's an early picture of the lava dome, the whaleback. And if we zoom in on this little area down here, just where it's coming out of the ground, and look at it in close up, you see these sort of striations, these vertical lines. Any geologist that's looked at exhumed earthquake faults will look at that and say, whoa, earthquake striations. They look like it. And in fact, the material is very much like fault gouge, the same stuff that you find in regular earthquake faults. Yet in this case, it's on the side of a growing lava dome. And this sort of bathtub ring like here, you go back day after day and you see that it's moving up. And it's moving at a rate of around 5 to 8 meters per day. So this is a very active system. And of course, we're getting earthquakes every minute or so. It makes sense. So maybe that's what those things are. There's another view of the lava dome. You can see even on a larger scale these striations. Okay, here's an example of one of the seismograms recorded close up, and I put a soundtrack to it. Can you hear that? It's speeded up by a factor of 50. And so you're hearing an earthquake about every minute, but speeded up, it's occurring about every second or so. That's the close-in station. A station only a few kilometers away. Those same events don't look like isolated events. They look like what's called volcanic tremor. Good example. Maybe volcanic tremor is nothing more than a whole bunch of little tiny earthquakes back to back, so close that by the time the waves are dispersed and travel a few kilometers, they all merge together and become volcanic tremor. Another process figured out. Well, those sorts of earthquakes that we've come to call drumbeat earthquakes, because they're very regular, bang, 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 they keep occurring and are relatively small compared to some others that are much larger. Here's an example of another one of these types of seismograms that's showing the two different classes of earthquakes. The frequent and small drumbeat earthquakes, and then the less frequent, sort of randomly spaced, larger earthquakes, magnitude 2.5 to 3. By the way, the colors on these plots are put on there only to aid your eye in separating different lines. They have no other significance. So each line has a different color just for visual help. But you can see there's a number of these larger earthquakes taking place. They seem similar to the drumbeat earthquakes, but they're much bigger, and they're not nearly as regular. And they only occur over certain time periods, maybe a few days, for example, in December, and then again in January, and again in April, when we're seeing these big earthquakes. But there must be a different sort of process. Well, we discovered that if we look at sort of when those occur, and this is showing the background level of the seismicity going up and down, and there were a couple of periods in which the activity would build up and then suddenly get low again, and build up and then get low again. I'm going to show you some photos taken about a month apart during this period. The first one during one of these build-ups, then another one taken after that when it's low again, and then later on when it's sort of built up and gone down again. Now this photo is taken from the rim of the volcano looking down on the new lava dome. And this is, of course, a nice whaleback. This is during one of these early build-up periods before we've had the big, isolated, independent, large earthquakes. Those took place, and then a month later, this is the way that looked. That whaleback has now been broken up. It's now in pieces. There's a few isolated chunks of it there, but it's essentially fallen apart. So we've realized these big earthquakes seem to take place during periods when the dome is breaking up. So what does that tell us? We're not sure yet. A month later, we can see in this area, the dome is yet again growing again. The broken up part is just sitting there. It's actually subsided slightly, but this part is growing. And this was taken less than a month ago, this picture, and this is more or less the way it is today, though this is now a little bit higher. Well, I'm going to show some other types of photos to convince you that this thing really is growing, even though it's slow and it looks like solid rock. It's not. There's a time-lapse type of camera located just outside the crater at Sugar Bowl that has a view like this, looking in. So in the foreground in this area is the old dome, and the new dome is around behind it. So here is the old dome, and just peeking over it early on is the new dome back here. So I'll show you a series of pictures. This is later on. This is this winter. Here's the new dome. It's gotten really big. And I'm just going to flip through a few pictures fairly quickly. Keep your eye on it, and I think you'll be able to see the motion. Okay. Sampling. This was only done once. Helicopter landed, the volcanologist jumps out and runs up the hill to the edge of the lava dome to get a sample of that fault gouge. I thought I'd just throw this in to show that this probably wasn't a good idea. This was before there were any of the explosions that have taken place. There have been 3 relatively mild, but certainly dangerous explosions since then. And sampling now is done by taking a bucket on the end of one of those lines on the helicopter and just scooping it up and boogieing out of there. Photogrammetry, taking aerial photos, looking down on the volcano, turning that into a digital elevation model, and then illuminating that artificially so that you can get a shaded relief map is an interesting process to go through. And we'll run through a series of these to look at how the volcano's changed. This is a combination of actual regular conventional photography as well as sort of a new imaging technique called LiDAR, in which rather than using just available light and pictures, you shine a laser down and watch the laser bounce back from the surfaces, and you generate an image from that. And a combination of these two has been used for these digital elevation models. Sort of an empty crater in 1980 after the big eruption, and a very small dome had started that winter. By 1986, that dome had gotten quite large, and it's mostly filling the central part of the crater. Well, by a couple of years ago, it looks like it's grown smaller. Well, that's really not the dome growing smaller, but it's ice and snow filling in, generating a glacier all behind or on the south side of the dome here. And if we flip that up on the side, we can sort of see how much is done there. There's the 1986 surface at the bottom. You can see where the ice is. So you can see only a part of the dome is still exposed above the ice now. So this is a complexity to this eruption, which has been generating a lot of problems, because how do you then determine how much volume is involved in the new? If it's melting the glacier partially and replacing it, you won't see changes. We don't think that's happening very much, and we're actually, the deformation we see is representative of the new material coming in. But there's always some question how that's working. So now if we go from before the latest eruption began, and we'll step through at roughly month intervals and watch the dome grow. And it generates a nice whaleback here in November. Late November, it looks pretty good. In December, it starts to break up. By January, it's broken up. We've gone through one of those periods with the big earthquakes, and it's broken up somewhat. Starts growing again, and in February, it's looking like a nice whaleback. Late February, it's nice. By March 10th, it's looking pretty good. By April 19th, it's broken up. And that's the last one of these we've had. There's been more photos flown, but the processing takes some time to run through and generate these. The crew of the USGS in Denver does most of that work. But if you plot the differences of those, or how much volume is involved here, you can see we've got a pretty nice type of curve, how this is going. Early on, the growth rate was on the order of 7 or 8 cubic meters per second. It's now down to about 1.5 cubic meters per second. So that's a cube about this size on a side being plopped down every second. Another cube is being added. Blang, blang. And that's now going on, and apparently will continue at least for a while. So it's gotten pretty big. Where will this go? Well, back in 1986, several volcanologists plotted curves through the dome as it was being built then. And then you could extrapolate those based on those curves, and you might get, well, you're probably not going to get this. The early growth was very fast, so this curve is probably not right, because the later dome growth seems to match this type of curve better. Depending upon whether you put a second order polynomial through it or a linear fit just to the last part, you come out with this type of prediction. Well, here are the points that are now being added. And at that rate, the latest is about 50 million cubic meters being added to a dome that was roughly 70 million cubic meters. We've got maybe about 65 million cubic meters to go. And since the rate is declined now, if it continues, it might be as much as most of another year before it catches up. Or if it just keeps going at this rate, it would be maybe a decade to 15 years before it mostly refilled the crater and you had a St. Helens similar to what it was before. Well, that's sort of the St. Helens story. We'll finish up very briefly talking about a few of the other volcanoes. And as a seismologist, I'll have to do so using seismology and look at what the seismic rate of activity is at these volcanoes by just counting how many earthquakes occur right under them at any given time. And St. Helens usually is the winner. There have been periods of time when it's been relatively quiet, but mostly it is still the most seismically active and, of course, the most volcanologically active as well. Next to it are Mount Rainier and Lassen Peak in California. Both of them have a modest amount of seismicity going on all the time there, and then decreasing amounts. But what about the hazards for these? What are the dangerous ones? Well, really the most dangerous are Mount Rainier, Mount Shasta, and Mount Hood. And that's because of the population there. St. Helens is really not dangerous. No one lives nearby. There are not very many people that go in close to St. Helens, particularly when you got this type of warning. The Forest Service can restrict access. Other than aircraft flying over it and getting bonked by a rock or ash, there's really not a lot that can go wrong there now. Mount Rainier is a whole other story. Very different sort of beast. It's pretty close to population areas. There are a number of towns and villages in the valleys just beneath it. They are definitely well in harm's way from that volcano. It's much bigger than St. Helens. There's lots of ice and snow up there. It's very steep, has unstable sides. It could be a very bad player. Several years ago, the National Research Council essentially authorized a book on it, and notice the title, Mount Rainier, Active Cascade Volcano. It's considered an active volcano. It's not erupting at the moment. It will erupt again, and it has frequently in the geologic past. And so it must be considered a serious contender, much worse than St. Helens. The seismicity there, it comes in two flavors. There's earthquakes that are in what we call the West Rainier seismic zone, represented by the green symbols here along the west side. These earthquakes may be only peripherally related to the volcano itself. They may be primarily tectonic or an interaction of tectonic and deep-seated magmatic stresses. But the players that we worry about are represented by the reddish symbols right under the central part of the cone. These are shallow earthquakes that are within the cone. The types of events, should they occur in increasing numbers, that we would be convinced were pre-eruptive indicators. And so we do monitor Mount Rainier very carefully. Why it's a bad player? Well, this is just an example. I mean, there are a lot of places like this, but this is maybe the worst case, is a village named Orting, which is down in this flat area between the Carbon and the Puyallup rivers. And there's a reason that's a very flat area there. If you go down there and dig around in it, you will find big stumps of trees that were killed about 500 years ago. And some of them were knocked down and then buried. And these are trees that were a forest growing there when a mud flow came off Mount Rainier and wiped out this whole area. Fairly good-sized mud flow. And the thing that is disturbing to many of us is that there's not an obvious major eruption of Mount Rainier taking place at that time. It may have been a fairly minor event, possibly even spontaneously going on its own, that a big section of the west side of the volcano fell off, went tearing down the valley, turned into a mud flow or lahar, traveled all the way down to Puget Sound through what is now populated areas. There are probably close to 100,000 people that live in areas at risk around Mount Rainier. Well, I'm going to just finish up a little bit with how things have changed and come back to what maybe will be of interest to you in the future. 25 years, the computer is probably one of the major differences. Obviously, there's other instrumentation improvements and new types, but the differences in the computer processing is really dramatic. With the beginning of the eruption in 1980, on March 20th, we had just installed and started running our very first computer recording system on March 1st. So we did capture many of these earthquakes digitally back then, but that was the very beginning of the computer age and volcano seismology. Today, the same types of computers are about the size of your finger. Or, the laptop here is 50 times more powerful than the computers that we were using back in 1980. That's not news to anyone that these types of changes have taken place. Back then, our primary recording, though, for doing analysis was visual. And it was these records, like you saw before, that you had, and if somebody else wanted to look at them, they had to come in and look at that record. Pictures of the volcano were taken with film, and to show them to other people, you had to go send the photos through the mail or whatever. Now all the data is available to anyone in the world almost instantaneously via the internet. So the internet age is here. We've gone from needing to be in the office all the time. We had people manning the thing around the clock, to letting the computers do a lot of the processing and automated stuff for you. It'll call me up on my phone and say, I think you better look at this. I can roll out of bed, go to my computer, dial it in, look at it, and go back to sleep because it wasn't important. And in fact, you can do that too. Almost everything you've seen here that is current, you can find on either our website or the USGS Cascade Volcano Observatory website, both of which are linked together in many ways. And so you can look at the seismic data, you can see many of these photographs that are occurring, and you, in fact, I can report we get lots of email from people, and sometimes those emails point out some things that we have not seen yet. Now, we're not embarrassed by that. We think this is a good thing. This is participatory in the sense that anyone can contribute. And in fact, Ruth Ludwin, sitting down here in the front, is our recipient of this, and she may not think this is such a great idea always, because some of the email is not necessarily very, shall we say, relevant. But now and then there's really useful stuff that comes in, and so we don't mind that at all, and we think it's part of our duty to provide this information for you. So, in finishing, I'd like to thank particularly the scientists of the Cascade Volcano Observatory, my colleagues down there. Many of the things I've shown here are due to them. Of course, the staff of our Pacific Northwest Seismograph Network. Funding comes from the USGS, and of course our home is in the Department of Earth and Space Sciences. So, questions? Yes, over here. Okay, the question is how deep are the deepest seismic events ever detected? Well, the deepest earthquakes anywhere in the world usually are on the order of 600 to 700 kilometers deep. And these are only in a few isolated places. Now, the deepest earthquakes under a volcano like this, and particularly in our case, have been around 20 to 25 kilometers deep. So all of the seismicity we see associated with the volcanoes is really crustal. But on a worldwide scale, where you get big subduction zone systems going, very old ones, you can get earthquakes down exceeding 600 kilometers. The question? Yes?
The extremes in Chicago went back. How long do you see that in volcanoes in the eruption phase?
The question is the whale back I've mentioned. How often is that seen in volcanic eruptions? I don't think very often. I think I'm not that well versed in all dome building cases of volcanoes elsewhere, but I think a morphology that is that smooth and that continuous over that size, I'm not aware of any other place that it exists. I know there are some cases where as domes grow, at least parts of them are smooth for a while, but mostly they're far more jumbled and rough. I think this is somewhat unique, as I think is the seismic sequence that's going along with its generation. Yes?
Is there any connection or correlation between the Cascade volcano activity and the so-called slow volcanoes within Greenland?
The question is there association with the Cascade volcanoes and the so-called slow earthquakes?
Yes.
Is that what you're talking? Yeah. This is my second most favorite topic, are the slow earthquakes or deep tremor, a phenomena that is an amazing process. It's very quickly, I'll say what that is for those that aren't familiar with it. I mentioned earthquakes are the breakage of rock, and that usually takes place over the course of seconds to maybe tens of seconds to, for very large earthquake, a minute or so. But we've seen cases in both Japan as well as here in which it apparently an earthquake takes place over a period of 2 weeks, i.e. a very slow earthquake. It's so slow that it doesn't shake the ground. It's not hazardous at all. It's only detectable by using these geodetic measurements. You measure where a position is, and it moves just a few millimeters over the course of a few weeks, and you have several of these. You can model that in terms of fault slipping at depth. And this is taking place roughly every 14 months in northern Puget Sound and southern Vancouver Island. And along with it, we're seeing now tremor, very much like what I showed you here on the volcanoes, except this is called non-volcanic tremor. And it's coming from a depth of anywhere between 20 to maybe 50 kilometers deep in the same area where the slow earthquake is occurring. This is a brand new phenomenon. It only was discovered a few years ago. And it's not only this strange slow process, and has the tremor going along with it from time to time, but it seems to be very regular in time, every 14 months. The next one is scheduled to occur roughly August, September. So keep your eye on the newspaper or our web pages for information about when that occurs. Now, your question, is there a relationship between the volcanoes and these? Apparently not, other than these slow earthquakes do take place on the subduction zone. The subduction zone, after it goes down deeper, is the source of the magma that generates the volcanoes. So indirectly, they are vaguely related, but it doesn't seem to be any temporal association. They're actually separated in distance by several hundred kilometers. So a direct relationship, no. But these deep tremor, slow earthquakes, there's a very mysterious new phenomena that we don't know very much about yet. Stay tuned. Other questions? Yes?
Do you think the other Cascade volcanoes need additional monitoring?
Yes. We always need more monitoring. I'm a seismologist. We need more seismographs. Actually, that's the question is, do the other volcanoes need more monitoring? Indeed, the USGS just recently came out with a report that ranked all of the volcanoes in the U.S. and their territories as to their hazard and how well they're monitored. And there's about 160 volcanoes total put together. Many of the Cascade volcanoes pop up very high on the combination of pretty high hazard and under-monitored. And the hope is that we will get improved monitoring over the next several years at a number of these. Certainly Mount Rainier. Mount Rainier, we do have about a dozen seismograph stations. It's hard to keep some of them going. We lose them in the winter sometimes. There's lots of logistical issues in operating them. And it's a very important place to keep the monitoring going. I feel we could do a better job, and I'm hoping we will. Okay, I think that's probably a good stopping point. Thank you.
Thanks, Steve. That was wonderful. So in closing, I would like to thank several co-sponsors that made this whole lecture possible, starting with the Pacific Northwest Seismograph Network. Steve is the acting director of that, and that is the system that monitors the volcanoes and other earthquake events throughout the Pacific Northwest. So that's a very important center to recognize and to help support activities related to that center. Again, the Earth and Space Sciences Department, who makes this possible, and the University of Washington College of Arts and Sciences, who also is a co-sponsor of this program, USGS, and GeoMap Northwest. The Cascade Range of the Pacific Northwest has more than a dozen potentially active volcanoes. Cascade volcanoes tend to erupt explosively, and on average 2 eruptions occur per century. The most recent were at Mount St.Helens, Washington, and Lassen Peak, California. To help protect the Pacific Northwest's rapidly expanding population, USGS scientists at the Cascades Volcano Observatory in Vancouver, Washington, monitor and assess the hazards posed by the region's volcanoes. The volcanoes of the Cascade Range, which stretches from Northern California into British Columbia, have produced more than 100 eruptions, most of them explosive, in just the past few thousand years. However, individual Cascade volcanoes can lie dormant for many centuries between eruptions, and the great risk posed by volcanic activity in the region is therefore not always present. Mount St. Helens is the most frequently active volcano in the Cascades. During the past 4,000 years, it has produced many lahars and a wide variety of eruptive activity, from relatively quiet outflows of lava to explosive eruptions much larger than that of May 18, 1980. The more than 1 million residents of the Seattle-Tacoma, Washington area live in the shadow of 14,000-foot Mount Rainier, the tallest volcano in the United States outside of Alaska. Several communities near the volcano, built on the deposits of giant lahars, are at risk from similar future lahars. These enormous mudflows of volcanic ash and debris are less than 1,200 years old. Mount Rainier has produced at least 4 eruptions and numerous lahars in the past 4,000 years. It is capped by more glacier ice than the rest of the Cascade volcanoes combined, and parts of Rainier's steep slopes have been weakened by hot, acidic volcanic gases and water. These factors make this volcano especially prone to landslides and lahars. Therefore, Mount Rainier is considered more dangerous than Mount St. Helens, and many downstream cities have early warning systems to detect these disastrous volcanic mudflows.